So good afternoon, everyone. We are back with the presentations. The next one is the presentation by Unai Atxitia, Ultrafast magnetism and Thz Spintronics. Unai is a group leader at the Department of Physics of the Freie University of Berlin. He is involved, his work is related to the theoretical description of spin dynamics in nanoscale systems. Unai did his PhD in Madrid in the Institute for Material Science under the supervision of Oksana Subikalo. And then she went to York as a postdoc, and she worked with Roy Chantrel, a very well-known person in this field of magnetization dynamics, nanoparticles, and different type of nanostructure materials. She also worked at the University of Constance after that with Professor Novak, also a very well-known person in this field. So she has a lot of experience in the study and in the use of different theoretical tools for the study of this ultrafast dynamics in magnetic nanostructures. He focuses on the use of thermal gradients and laser pulses to induce these changes in the magnetism of these nanostructures. So it's very his research goes very well in the topic of this afternoon about this specific effect and all this magneto-spin dynamics. It's my pleasure to introduce you then to Unai, and she will talk for the next 50 minutes. Unai, if you agree, I will give you a warning when you have 5 minutes left. Okay, so please go ahead.
Okay, let me share my screen, sharing. So you can see my presentation, just my slides. So thank you for the introduction, and also thank you the organizers, yes, especially Fernando Bartolome, who invited me to give this presentation here. So I work, as you said, in Freie Universität Berlin, and there we have a collaborative research center about ultrafast spin dynamics, where we have 20 projects working on the understanding of spin dynamics at the ultrafast scale. So basically, we look at this spin and we want to understand how the dynamics happens. Yes, and we use, from the theory or experimental point of view, laser pulse. So we apply laser femtosecond optical pulses to the spin, and we look at how it moves. So this is my talk about, and so here you have 10 to the 12. So I would like to give you some time to think about this 10 to the 12. So what this number means to you. Yeah, so for us, this is like the objective to achieve within this project, to have 10 to the 12 bit operations per second. So if you think about Spintronics, current technology can achieve 10 to the 9 bit operations per second. So this is 3 orders of magnitude faster. Just so, but today I'm going to try to talk about some basics. So on these topics about Thz Spintronics and ultrafast magnetism. So let's start with the electron spin. So within the classical picture of a spin, the spin is the angular momentum of a rotating electron, as you can see from the figure. And this creates a magnetic dipole moment that we all know. So spins in solids can order in several ways. So the most basic ones are ferromagnets, where all the spins are parallelly aligned, antiferromagnets, where the neighboring spins are anti-parallelly aligned, and Freie magnets, which are similar to antiferromagnet, but one of the sublattice has a different atomic moment. So why we deal with spins? So you already know that conventional electronics uses the electron charge to encode a bit, zeros or 1, and spin electronics or spintronics wants to use the electron spin as information carrier, like a magnetic hard disk. So in order to achieve, we need to understand 3 elementary spin operations. Turn spins around, transport spins to create spin currents, and use these spin currents to manipulate magnetic moments. Yes. So the goal of ultrafast magnetism and Thz spintronics is to understand and control these 3 operations at the picosecond time scale. So this is already possible. For example, one can switch the magnetization in the picosecond time scale in some specific materials, like gadolinium iron alloys, as you can see here. After applying femtosecond laser pulse, the magnetization of iron and gadolinium reduces. Iron switches the polarity and aligns parallelly to gadolinium, creating some kind of transient ferromagnetic state that lasts for a couple of seconds, and then gadolinium switches magnetization. So it's possible to switch magnetization in specific materials using just laser pulse. It's also already possible to create ultra-fast spin currents. This can be achieved in bilayers, for example, of nickel iron, where when you apply a femtosecond laser pulse to nickel, this creates an ultra-fast spin current that is injected into the iron layer, and the iron layer increases its magnetization in case they are parallelly aligned. In the opposite case, if they are anti-parallel, the dynamics of the iron layer reduces, yes, and accelerates. So this has been already demonstrated that one can manipulate magnetization in the order of sub-picoseconds. Okay, so in this talk, I'm going to give a brief introduction into some general concepts of ultrafast magnetism and spintronics, plus a couple of examples. So I'm going to start with fundamental spin couplings, then how to exert the torques in the spins, and as examples, I'm going to show how can you induce spin dynamics in antiferromagnets and even switching. And finally, I'm going to focus on ultra-fast magnetization dynamics in 3D ferromagnets, in particular in nickel. Okay, so we can start with how a magnetic order can be described in a solid. So if we take 2 spins, yes, the interaction, the energy interaction, the energy can be described by an effective Hamiltonian, a Heisenberg Hamiltonian. And if the exchange interaction J1, 2 is positive, they align into the same direction. If it's negative, they align anti-parallel. Okay, this is just for 2 spins, but one can extend this model to more than 2 spins, and by summing up over the whole solid or lattice, these Jij are coupling parameters. They can be sometimes calculated from first principle calculations, or by mapping the results from the model to experiments. One can extract sometimes these exchange parameters. This model already describes well a magnetic order and predicts important magnetic phenomena. So now the idea is to rewrite the exchange coupling in terms of effective fields. So let's do this. We have this effective Hamiltonian. So we can write the effective Hamiltonian as the product of the spin, Si, by the effective field, that sees this spin Si and then sum over the whole lattice. In this case, the spin precesses around a global magnetization in a wave-like precession. So these are called magnons, and these magnons can be excited directly by some external stimulus or by thermal fluctuations. When you take into account temperature, the thermal fluctuations excite these magnons and reduces the global magnetization M, and we obtain this magnetization against the temperature curve, which is very well known. The magnetization decreases as a function of temperature until some critical temperature or Curie temperature, their magnetization is zero. So the thermal fluctuation can act against exchange interaction. However, exchange is isotropic. So the question is, what sets the direction of the magnetization? Yes, the most simple example is a magnetic field. So if we put the spin into in the presence of a magnetic field, then there is a Zeeman torque. Yes, here this term corresponds to the Hamiltonian of the Zeeman torque. This and the spin will align along the direction of the external field B. Yes. An external magnetic field can be created by a coil and to write information, for example, in hard drives, or a magnetic field can be also created by surrounding spins by dipolar interactions. Spins can also couple to electric fields, right? So if an electron is moving in the presence of an electric field, this electron sees the spin orbit field, and this creates a spin orbit field, yes? And from there we can write a simple Hamiltonian, the spin orbit Hamiltonian, yes? And spin orbit coupling, I guess that you have already listened about this before during this school, has important implications, yes, such as magnetocrystalline anisotropy that can favor out-of-plane magnetization. This is very good for higher bit density on hard disk. Also, it's related to the spin Hall effect, magnetoptical effects. But in here, we are interested on the spin orbit torque. The electric field can drive magnetization dynamics. So let us summarize these all spin couplings that I have presented. So what you have is an effective Hamiltonian. So H spin it's multiplied by an effective field, which contains Zeeman coupling, spin orbit coupling, and exchange coupling. So these fields act like an effective field, just acting on this spin Si. So if we can use this to induce magnetization dynamics by changing these fields, the spin is going to follow this internal field. Yes. So what determines spin dynamics? So we have to consider an equation of motion for the spins. So in here, the equation of motion, this is just the commutator of the Hamiltonian with the spins, but basically it's the dynamics is defined by the cross product of the spin at the side I, yes, by the effective field acting on this spin. So this is the total torque on the spin Si, yes, which again, it contains Zeeman, spin orbit torque, and exchange coupling. So this is exactly the handle to ultrafast control over magnetic order. So we can control the spin dynamics by an external magnetic field, an electric field, or indirectly by modulation of coupling parameters using light, current, or heat. Okay, so now first example is ultra-fast Zeeman torque by an external field. So the natural stimulus in magnets is a time-dependent magnetic field. Yes. So we can use a terahertz pulse. Yes, that is just an electric field with this shape on as a function of time, and this electric field is, comes with an external magnetic field with the same time dependence, and when we put this external field in presence of spin, this creates a Zeeman torque. Yes, so if we have our solid represented by these two spins, so the spins are going to be at equilibrium aligned along this internal effective field. When we apply a terahertz pulse, what is going to happen is that the spins are going to go out of equilibrium, yes, and afterwards the spins are going to go back to equilibrium by precessing. Okay, so the most efficient way to couple electric field or magnetic field to the spin dynamics is to work on resonance. Yes, so this is the Larmor frequencies, the characteristic frequency of the system, and this scales with the internal fields. In ferromagnets, these frequencies are much less than 1 terahertz, is on the gigahertz regime, but in antiferromagnets, they can go up to several terahertz or terahertz regime. So now let me explain you why are these precession frequencies so different, or what is the origin. So when we have a ferromagnet and we apply an external magnetic field, so the spins align along this external field, and they can remain parallel. Yes, there is no work against the exchange interaction, so the energy of this configuration is rather low. In antiferromagnets, if we apply a magnetic field, then the spin 1 is going to align along the external field, but the spin 2 should turn and make some work against the exchange interaction. So the spins are not going to be anti-parallel anymore. Some work is going to against the exchange interaction has to be made, and this creates that this configuration has larger energy, so larger frequencies. So now the idea is we use terahertz pulses in antiferromagnets, yes, to excite this fast dynamics. Okay, so there are already experiments using these terahertz pulses. Yes, and this is what I'm going to discuss now. For example, this was a seminal work by the group of Tobias Kamprad. He's a professor here at the University of Berlin, and his group demonstrated that one can excite the spin dynamics in an antiferromagnet, in this case nickel oxide, using a terahertz pump. So what they did is, as using the figure, to use an incident magnetic pulse. It's of the order of 1 to 2 picoseconds. If you look at the frequency bandwidth, this is around 1 to 2 or even 3 terahertz. So, and this nickel oxide, it has a magnon at 1 terahertz. So the idea was to apply this incident magnetic pulse and see if they can excite dynamics. The dynamics can be measured with an optical probe via the Faraday effect. So they measure the transmitted light, the polarization of the transmitted light, and this scales with the magnetization. So what they observe after applying this incident magnetic pulse is that they could induce a very fast precession of the magnetization. So with a frequency of around 1 terahertz and a decay time of 40 picoseconds. So this is a clear signature of K equals 0 magnon at 1 terahertz. So one can think that, okay, antiferromagnets are very fast, yes, differently to ferromagnets. And so maybe we could use antiferromagnets to switch the magnetization much faster than in ferromagnets. Yes, so these ferromagnets are the switching process is slow, it takes nanoseconds. However, since we have seen that antiferromagnets, they have higher frequencies and picosecond timescale decay time, so one would expect to have a faster switching of magnetic states. Yes. So the idea now is to use electric fields instead of B fields, because electric switching of an antiferromagnet has been already demonstrated in copper manganese arsenide, and I guess this was part of the topic of antiferromagnetic spintronics during this school. So the spin couples to the spin orbit fields created by the electric currents and switches the magnetization by 90 degrees. So and then you can measure this switching by looking at the anisotropic magnetoresistance. So when the order parameter of the antiferromagnet is perpendicular to the electric current, the resistance is higher. So as a follow-up work, what they did is a group of Jung, Beard, and Kamfrat. They work together and they look at the possibility of switching the magnetic order in antiferromagnets using a time-dependent voltage pulse. And if you look at the figure, this pulse is of around a microsecond. Yes, so this is like 10 to the 6 a million times larger than a picosecond. And what they observe is that after applying one pulse, the magnetoresistance increases, and if they apply more pulses, the magnetoresistance increases even more, and this is a signature that the number of switch domains has increased. Yes, so what they did next is, instead of using a megahertz voltage pulse, to use a terahertz electric pulse. Yes, so if you look at the figure of a free space terahertz pulse, you see that this is a million times shorter. Yes, the shape is similar, but 10 million times shorter. So what they observe by looking, after applying this terahertz pulse, or a number of terahertz pulses, they look at the magnetoresistance, or the dynamics, or how the magnetoresistance changed with each pulse. And what they observe is that the pattern is the same, or very similar to what they observe with megahertz voltage pulses. So this is a signature that just with a terahertz pulse, you can induce magnetization switching. Here the problem is that still they are working, and we are working here in Berlin to look at the dynamics and the picosecond or subpicosecond dynamics of this process. So these works have started the ultrafast spintronics with antiferromagnets and the subfield of switching, yes, of ultrafast switching of antiferromagnets. Okay, so this is the main objective. So so far we have I have demonstrated or showed talk about how to push spintronic effect to the ultrafast regime by just increasing the driving frequencies to 1 terahertz. Yes, so we have seen two examples of driving force, say magnetic field or an electric field. This can be achieved using a terahertz pulse. Yes, in this case, what you need is a pulse where the electric field contains the frequency that you want to excite. Yes, and this is what we have seen so far. And now if we use optical pulses, in this case, instead of having the driving force, the magnetic field or the electric field, the driving force is the intensity. So what you need is that the bandwidth of the electric field has to be larger or equal to the energy that you want to excite. Okay. So in the rest of this talk, I'm going to just focus on excitation of magnetization dynamics using optical pulses. Yes. So where is the optical light absorbed primarily? So if we consider a solid, yes, so what we have is three basic subsystems: electrons, spins, and lattice. Okay, so in metals, absorbing materials, this dynamics is induced by the deposited heat, yes, which scales with the intensity of the electric field, and it's the electrons that absorb the energy, and the electrons are heated, yes. So this optical excitation of metals and the understanding of this, the complex responses of these metals to a optical pulse is known as ultrafast magnetism or femtomagnetism. So this is the what I'm going to talk in the rest of this talk. So this field of femtomagnetism started with the discovery by the group of Borreper and Bigot in Strasbourg 25 years ago, that when you apply a femtosecond laser pulse, the magnetic response is the magnetic system responds in the sub-picosecond time scale. So what they observe here is that the magnetization reduces to the half of its value in the order of 1 picosecond, and then the magnetization recovers. Yes, so this was in nickel 25 years ago. Okay, and so since then we have been, or many people have been investigating, including me, nickel, yes, and other 3D materials and many other magnetic materials. Okay, so for example, if we want to understand these three systems, we have to look at the dynamics of these three systems separately, and then how they are coupled. So for example, if we look at the electrons, yes, well, one can use photoelectron spectroscopy to measure the electron temperature dynamics. So what these experiments can do is to look at the distribution of the electrons around the Fermi energy, and from there they can fit the distribution to a Fermi-Dirac distribution and obtain the effective electron temperature. What they observe is that after applying a femtosecond laser pulse, the electron temperature increases up to 1,000 or 2,000. It depends on the fluence of the laser pulse, Kelvin. You know, so after 200 femtoseconds, the electrons are very hot, and then this electron temperature decays on the order of 1 picosecond or half of picosecond. Yes, this is common in magnetic materials. Then there is a very new technique, which is electron femtosecond resolve electron diffraction, which has been developed here in Berlin within the project of ultrafast spin dynamics, and they can measure the lattice dynamics by studying the diffraction patterns. And what they see is that the lattice temperature, there is no peak, it just increases, yes, like an exponential increase with a time constant of around half a picosecond, which corresponds, so these two figures correspond to nickel, and the rising time of the electron temperature is similar to the decay time of the electron temperature. Yes, so they are related. And finally, electron, the spins, the spin system. Still, there is no a technique to measure the spin temperature, but what you can use magneto-optical effects, yes, like a Kerr effect, to measure the dynamics of the magnetization. Yes, for example, you can see here how it looks, the dynamics of nickel in using the magneto-optical Kerr effect. And if you look at the dynamics of the electrons, you see that this decay of the transient Mach signal is similar to the increase of the electron temperature. And then in the transient Mach signal, so the magnetization, there is a recovery that also corresponds partially to the decay of the electron temperature in the electron system. So how can we understand this dynamics? Yes, is maybe the next question. So this was already proposed 25 years ago in the seminal work by in nickel. Yes, and it's the 3 temperature model. So we consider that we can consider that electron spins and lattice they can be described by a temperature. Yes, it's one different temperature. So if we see here, there are three equations, yes, one for each temperature, and these equations they contain 2 coupling parameters. So the electrons coupled to the spins to the lattice, the spins to the lattice to the electrons, and it's within this model, it's assumed that the electron system, yes, absorbs the energy. This PT is the energy, the heat from the laser. So this is like a Gaussian profile. The electrons absorb this energy, and if you look at this orange curve, the electron temperature increases. And then if you look at the second equation, which corresponds to the lattice, since they are coupled via electron phonon coupling, the electrons transfer energy to the lattice, and the lattice starts to get heated, yeah? So to increase its temperature, and the same happens to the spins. Yes, there are also some couplings between a lattice and the spins, and so on. But the main contributions are the electron phonon coupling. Okay, and this is the 3 temperature model, very basic and phenomenological model that has been used, and it's already a model that people are using. So in this model is defined by the specific heats, yes, CE, CL, CS, and coupling parameters. Okay, so and here I wanted to just present you a work that we did in Berlin, which is about constructing a simple model, yes, for nickel, starting from this 3 temperature model. Okay, in collaboration with some theory, one theory group, yes, from Professor Waberger in Dresden, where they calculated the parameters for nickel, the heat capacity of electrons, lattice, and electron phonon coupling. Okay, they calculated this from DFT calculations. So if you look at the figure, the heat capacity, basically the lattice, the heat capacity is constant above room temperature. So we work at above room temperature. The electrons, they follow a linear dependence on the electron temperature. This is very common to assume, because this comes out from the free electron approximation. And spins, they show a critical behavior around Tz, which is very common. Just okay. And the electron phonon coupling is not constant, but has well, some dependence increases with the electron temperature. This is not a general, but particular to nickel. But the important point is that this is the strongest coupling parameter. Yes. So what we did is just to investigate this 3 temperature model, just from starting from the most simple case. So what we did is just to assume that we have a 2 temperature model. Yes. So we know the specific heat of the electrons, the specific heat of the lattice, the electron phonon coupling from the DFT calculations. We know the laser pulses, the energy that we put into the system, and we have so we have no fitting parameters. Yes, and then we have these nice guys, the group of Ralph and Stoffer and the Fritz Haber Institute, where they have developed this femtosecond resolve electron diffraction technique. So we can check the lattice dynamics, yes, directly from experiments in nickel. So they have developed this technique, yes, and which basically what we did is, or they did is to put a nickel sample, 20 nanometers, then you just you excite the system, yes, with an optical pulse that goes into the electrons, hits the electrons, and then you look at the lattice by sending electrons. Yes, these electrons will create a diffraction pattern in transmission, and by looking at this radial distribution of this diffraction pattern and how it changes on time, we can extract the lattice dynamics. So, but let me maybe explain you this a little bit more in detail. So this is what they obtain. So before excitation, this black line, and after excitation. So this is, if we look at the peaks, they are a little bit different. So if we zoom in, there is a different in the peak height. Yes. So, and this is how it looks. This difference, this change in the peak height. Yes. As a function of time, we can translate this, or they can translate this into a change in the mean square displacement of the atoms, and by assuming thermal phonon distribution, obtain the lattice temperature as a function of time. Okay, so as I said, we wanted to use just the most basic 2 temperature model to check the parameters and the ultrafast dynamics of the lattice, and to make it simple. Just we have these the heat capacities from the electrons and lattice, and it's their temperature dependence, electron phonon coupling, and these are the experiments. Just so what we did is just to plug in all these parameters and calculate the dynamics of the lattice. Yes, and this is what we got. Okay, so this 2 temperature model is too fast. Yes, the time scale of this electron phonon relaxation is given by the electron phonon coupling, but also by the heat capacity of the electrons in the in the equations. Yes. So what we did next is to make this the model a little bit more complex, but just by adding to the electrons the heat capacity of the spins. Yes. So what we did is still a simple 2 temperature model, but in this case we added the specific heat of the spins to the electrons. Yes, and if you remember, these electrons plus spin, they diverge or increase, yes, diverging around the Curie temperature, and since the electron system goes above the Curie temperature, so the sum of electrons and the spin is larger than the only electrons and increases a lot. So the effect is that the dynamics of the lattice temperature reduces, and what we did once we introduced this the specific heat of the spins into the model, we obtain a perfect agreement. Just and not only for one fluence, but for all fluences that we investigated experimentally. Okay, so now this is what we obtained. The experiment and was about the lattice dynamics, and we can reproduce the lattice dynamics with a very simple two-temperature model, including the spin energy. Okay, we obtain also from the model the electron temperature, which goes above the Curie temperature. Yes, and if you look at the magnetization dynamics, what you could do is just to take what magnetization corresponds to this electron temperature. When the system, the electron temperature is above Curie temperature, the magnetization should be zero. Yes, if we look at this magnetization as a function of temperature, when the temperature is above 630, then magnetization should be zero. So this model doesn't capture the magnetization dynamics. Yes, so this we need to describe the spin dynamics properly. So one way to describe the spin dynamics within this context of ultrafast magnetism is to use an atomic spin model. So instead of considering spin temperature, we consider a lattice of a spin where the energy is given by the Heisenberg model, and the dynamics is described by the Landau-Lissip-Gilbert equation. Yes? So each spin in the lattice, for example, we have like 5 million spins, is described by this equation of motion. Okay, this equation of motion contains mostly an exchange interaction, exchange field, plus thermal fluctuations. Okay, and this is how it looks, the dynamics of one spin. So it processes around the effective field with some frequency, and the thermal fluctuations just make this path of precession towards the equilibrium like noisy. Within this model, one can describe equilibrium properties, and it's usually used to describe ultrafast spin dynamics. Yes. So what we did is to substitute the spin system instead of having a spin system coupled to the electrons, to use this model to calculate the energy transfer from the electrons to the spins and from the spins to the electrons, and at the same time obtain a macroscopic view of the spin dynamics. Yes, so with this model we can also describe correctly the lattice dynamics. Yes, and here you see this red line are the theory, and the symbols are the experiment. So we can describe this and also get access to the microscopic spin dynamics. So in here, we see how the energy of the spin system evolves. Yes, so this solid line is that when we apply the femtosecond laser pulse, the spin system increases energy. And why increases energy? Because the system starts to get disorder, and this exchange energy increases. Yes, as we can see here, after we apply the femtosecond laser pulse, we see that the set component of its spin points to a very different directions. Yes, but once the system starts to cool down, yes, the spins, they prefer to be parallel. So what they do is to start to form like magnetic domains. Yes, with system spins parallel to each other. And as the system cools down further, then all these domains start to align to the same direction, and at some point they go back to the initial state. So our model, yes, using atomistic spin dynamics, can have access to microscopic spin dynamics, and this model is very common within this community. Yes, so I have so I presented you this consistent model for nickel, which contains all the ingredients that usually are used in the field of femtosecond magnetism. So we have the electron, spin, and lattice, yes, and they can be measured with different techniques, yes. If we look at the electrons, photoelectron spectroscopy, this is how it looks in the experiments, the dynamics in nickel. So we also compare the electron temperature, yes, that we obtain from the model to these experiments, and we obtain that the agreement is very good. At the same time, we look at the dynamics of the spins from this experiment, and it's not perfect, but it's the agreement is good. And finally, the electron, as I have shown you, we obtain a very good agreement, yes, to the lattice dynamics. So I have just presented you a consistent model for a 3D ferromagnet, nickel. Okay, and yes, I think with this, I just come to my conclusions. So ESpinRed can be passed to the ultrafast regime by terahertz pulses. This was the first part of my talk, yes, and the force of torque is an applied field, yes. For example, you can use a terahertz pulse that contains electric field or magnetic field into antiferromagnets, which have this characteristic frequency or Larmor frequency that lies in the range of terahertz pulses. And I have showed you two examples. Yes, first example is induce of magnetization precession in nickel oxide by the magnetic field of terahertz pulse and switching of an antiferromagnet using the electric field of this terahertz pulse. And as the second part has been about femtosecond laser pulses, the optical pulses. In this case, the force or torque is the light intensity. So this optical pulse, this energy, this is absorbed by the electrons, and the electrons are heated, and this energy is transferred to the lattice and to the spins. Yes, and I have give you an example, which is kind of a paradigmatic because it was in the nickel, and which was the first magnetic material showing this sub-picosecond response to an optical pulse. And so I have give you some details of the theory models behind this dynamics. And with this, thank you very much.
Thank you very much, Unai, for this very nice presentation. And so now the talk is open for questions. And while people is thinking about the questions they're going to make, I will take the time and make one question. Okay, because we don't have questions still. So, you know, you said at the beginning, or I mean, the first part of your talk, when you talk about this terahertz pulse dynamics or induced dynamics, that you use antiferromagnets because of the faster dynamics, right? Than in the ferromagnets, because you don't have this restoring force due to the antiferromagnetic exchange. My question is, could this limitation with the ferromagnets could be overcome by using ferromagnets with a strong anisotropy, like exchange bias, in which, for example, coupling between the ferromagnet and some pinning layer or something will force the ferromagnetic state to go back to this position after the excitation, or I mean, it's no sense.
Yeah, so I think it makes sense, yes, because when you have this exchange bias, so at the interface, maybe you can generate some kind of a strong field, yes, and by exciting with a laser pulse, then this field could act, so like create, yes, a transfer field that makes the processional switching. So I think this is possible, and all this interfacial magnetism is quite complicated, yes, and adding this ultra-fast component yeah, makes it more complicated. But there are some recent works where they have used this combination of anisotropies in thin cobalt films, just like 1 nanometer or something. And instead of using laser pulses, what they did is to use an electric pulse, yes, of picoseconds. So what they do is to generate this electric pulse using a femtosecond laser pulse that with a photo switch that creates the electric pulse into this thin film. And by using this interfacial anisotropies, a combination of this, they could switch the magnetization. So yes, so with a ferromagnet, you have always to need to make it faster, to introduce another layer, something, but it's possible, yes. And I probably it's yes, for technological purposes, it's better to work with materials that works, yes, in usual spintronics.
Okay.
So you are right, yes.
We have one question from, I guess, Fernando Bartolome, FB. Thank you, Unai, for such a nice talk. Maybe this is a bit off-topic question, but would you expect new physics in future from attosecond pulses from free electron lasers? Would this new time range be too fast to follow for electrons and spins? Or would this change interaction follow that excitation?
So thank you, Fernando, for your question. So this is maybe it's too fast. I'm not sure. What happens with attosecond pulses is that what you are doing is just exciting charge transport. So there are some preliminary works on attosecond spintronics. And what you do is like moving spins from one spin. From, for example, they can jump from. So you have a majority, minority, and they can go to another lattice side. Yes, okay. And this creates some magnetization dynamics. So optically induced transitions from one side to the other, from minority to majority, and this is from my, it's not my field. And so if, for example, spintronics is too slow for me, ultra-fast magnetism is too slow for attosecond science. So
that's it. Okay. We don't have any other questions yet. So I will ask you, maybe it's not, I don't know, I mean, your colleagues in Berlin, I think they are the ones responsible for these ultra-fast lattice diffraction experiments, right?
Yes.
I don't know, you show this transparency in which they detected this tiny change in the intensity of the peak, right? Are these the diffraction peaks or scattering?
Yes, the diffraction, yes.
I don't know if I saw the slide very well enough, but I think did they also observe a widening of the peak? I mean, if this is a thermal effect, right? If I understood correctly, didn't you expect a broadening of the peak? Otherwise, the area is not the same, right? I mean, you only reduce the intensity, or I mean, you put this transparency very fast.
Yes. So what they do is they so what they do is to fit the whole spectra to some functions, yes.
Okay.
And then there are some fitting parameters, and each time they fit this whole spectra. And probably maybe there is this. Yes, you're right. Yes. So this technique is quite new, and I think they are the only ones with this femtosecond time resolution. Yes, there are others that they have like 1 picosecond, and it's true that, for example, some other people or the competitors, let's say, or whatever, they are looking to find in this broadening, I think, some anisotropy or something in order to look at the spins of the phonons. Yes, so they are looking at this as well. So if you can excite and find signatures of the spin of the phonons.
Awesome.
But yeah, so it's not super clear to me how do they fit this spectra.
Okay.
But I think it's very simplistic to say that it's just the height of the.
Yeah, probably they have a very complex function that takes into account everything in the whole spectrum.
Yes, yes, yes.
Well, it seems that we don't have any other questions, so I guess I will thank you again for this very nice talk. I enjoyed it very much, and it was very clear, and I hope the other attendees will enjoy it as much as I did. So thank you very much again, Unai, and for everybody else, we have this contributed talk session at 5:30, I think. Okay, thank you. Oh, sorry, there is a question, final question. Sorry, you're still there, right?
Yes.
Sergio Valencia. In ferromagnet has been observed a spin nutation with a terahertz frequency. Does this nutation also appears in antiferromagnetic systems with faster dynamics?
So I think this nutation comes from inertia of this, which usually there is no inertia in ferromagnets, yes, but I guess, so yes, they have excited ferromagnet and found a nutation. But when you look at the dynamical equations for antiferromagnets, so this inertia is there naturally, yes. So I don't know how to define this nutation in antiferromagnets, yes.
Okay.
So, but no.
Okay, so thank you very much. David Solomoni also says thank you for the talk, and I think that's put an end to your talk. So thank you, Unai. Thank you again.
Okay, you're welcome.